Hello everyone. On behalf of ISER Pune Optics League, I welcome you all to our webinar series. Today, we are glad to have Professor Síle NIC CHORMAIC as our speaker. Before handing over the floor to Professor CHORMAIC, I would like to introduce her to our audience. Professor CHORMAIC obtained her BSc and MSc degree from Maynooth University, Ireland. She achieved her PhD in physics from University Sorbonne, Paris, North France. After PhD, Dr. CHORMAIC achieved her postdoctoral experience at the University of Innsbruck, Austria, and the University of Melbourne, Australia. Then she also served Max Planck Institute for Quantum Optics as a visiting researcher. She also served as a lecturer and academic member at various institutes in Ireland like MTU, Tyndall National Institute, and University College Cork. Then in 2011, she joined OIST Graduate University, Japan, as an adjunct associate professor. And from 2016 onwards, she has been serving there as professor and PI. Her research spans the vast area of quantum technology, optics, optical cavities, and sensing. With this brief introduction, I would like to request Professor CHORMAIC to kindly take over the platform.
Okay, thank you. So you need to unshare. So thanks. Yeah. So I need to share here. So can you all see my screen?
Yes, ma'am.
Screen?
Yeah.
Okay,
yes,
so it should be fine. Okay, good. So I'd like to thank you for giving me a chance to talk to some students in Pune. Hopefully the time is okay. So it was harder to find a time when I was free because I'm teaching at the moment. So teaching is foremost in my mind at the moment, but hopefully I can focus on this for this seminar. And I'd like to encourage you, if I say something that seems to make no sense, try to interrupt me, because it's better that you understand something than I throw too much information and you understand very little. So if you want to interrupt me, because I know you'll all have slightly different backgrounds, so please do it. So I'm coming from OIST, which is a university in Japan, and I'm also part of our newly established quantum center, and where it's a virtual center, so just different people from the university join in this if our topics are somehow quantum related. So where is OIST? So we're located very far south in Japan, a member of this island chain called the Ryukyu Islands or Okinawa Islands. And the university is situated on the largest one of these islands. And you can see it there highlighted in red. And I just want to highlight a few things that the university can offer to students from international. So we're an international university, so we don't have any priority over nationality. All students, regardless of nationality, get the same treatment and the same funding. So we have a research internship program, which you're possibly familiar with. This is for students not on a master's or PhD program, so they are eligible for research internship. And we also have visiting research student program. This is usually for students who are already maybe on a master's or on a PhD somewhere. These programs are very competitive. So if any of you have applied already and didn't succeed, don't feel bad, okay? So we get so many applicants for every position that we know we have to reject very excellent students. It's no reflection on your quality if you've been rejected. Some more things that might be interesting if you're not a PhD student and you're looking for a PhD. So we'll have the next deadline in 31st of March. And if you are a PhD student, I'm working somewhere in quantum. So this can be cold atoms, this can be ions, this can be molecular physics, this can be solid state, this can be quantum optics. We run our annual summer school. So again, I have announced the website for this year. So this can be interesting for students from other places to come over and interact with us for a couple of weeks. So this is what our university looks like. So it's subtropical. So at this time of the year, some of the Indian students can feel it's a little bit cold because it's about 18 degrees. Summer, very hot. So but nice temperature for most of the Indian students. So I'm going to talk about optical nanofibres and research we do here. So I've been here physically in Japan since 2012. And I've been building up quite a large lab since joining. So my own background is in atomic physics. So first of all, I'll talk about some experiments on cold atoms, then on microparticle manipulation, which is a bit more accessible, cold atom experiments being so expensive, and then just some summary on where we are on the work. So optical nanofibres, I'm going to start out really basic. So what is an optical nanofibre? So we start off normal optical fiber. So we have light propagating through a fiber, and it propagates because we have two different materials. So we have the core and the cladding. So this is, if we assume just a normal silica fiber, the core will have a slightly higher refractive index than the cladding. And when light propagates through, and if we want to solve Maxwell's equations, we will see that at each reflection point, essentially, so if we think of a ray picture diagram, actually easier, each reflection point, there will be some small evanescent field, okay? But we don't see this in a normal optical fiber. Two reasons. First of all, the cladding is really big. So my size of optical fiber is about 125 micron. And this evanescent field region is extremely small. So it's just in the fiber as far as we're concerned. So this is a normal fiber, just taking a cut through it and half of the cross section. So here's my core. If it's a single mode fiber, it'll be somewhere around 5 to 9 micron. And then the cladding, typically 125 micron. But for some more exotic fibers, it might be going down as small as 80 or even 50 micron. And if I look at the refractive index profile, I just have a refractive index of silica and then slightly higher in the core and then silica again. Now, if I talk about the optical nanofiber, I have the very same scenario. So I have a core and a cladding. In this case, however, the core is the silica material. So its refractive index is the material that I previously had for the cladding, so 1.444 for silica. And the cladding now is whatever surrounds my glass fiber. So my fiber is really thin, just has a core, no cladding, but I immerse it in something. So it's sitting in air, or it's in water, or it's in some fluid. And that'll give me the refractive index of the cladding. So essentially the environment clads my core. And in this case, I have much bigger refractive index change. And what this means is that when light is propagating through my nanofiber, again, I'm going to get effectively in a ray picture diagram, total internal reflection along the glass core. But when I get into the environment, I will see the evanescent field. So the evanescent field before I said was confined in my glass fiber, but now the evanescent field is confined in the air, in the water, or wherever I've placed my fiber. So this is the typical shape of my fiber. I start off with a normal commercial fiber. I just buy it from some company, and then I fabricate ultra thin fiber in some region. So my ultra thin region here is usually a few millimeters. And if my mode is propagating through my normal fiber, when I start making the fiber smaller and smaller, that mode has to adjust itself. So it has to sort of fit into the fiber. And effectively, then this is where I get the evanescent field region going into the environment. And I like this diagram because I think it's pretty intuitive of what's happening. So if I have a fiber and its size is bigger than the wavelength, so in this case, it's like an 800 nanometer fiber and the wavelength is 633, it won't really give me any evanescent component. So most of the light energy will be contained within the glass fiber. As I go smaller, so here my fiber is about 2/3 the wavelength, I can start seeing more and more of the light energy is outside the glass fiber. And then if I go really small, I start to see that almost all the energy is now carried outside the fiber and very little of the energy sits in the fiber. So what I do is I operate somewhere between here, okay? I don't go too small, but I also want to have this evanescent field region that I can interact with. So how do I make them? Here we have a hydrogen-oxygen flame. We have some translation stages, and my hydrogen-oxygen flame is also on a translation stage. I just move this in under a section of my fiber. I've removed all outer coatings, and I just scan my flame. And while I'm scanning the flame, you can see it starts to glow red in a little, white in a little spot. I'm also pulling the fiber. So it's like if I'm pulling toffee or anything, it's getting thinner and thinner as I'm pulling it. So I just do that, and while I'm doing this, I monitor the transmission. So I'll have a laser connected at one end, and I connect a photodiode at the other end, and just monitor the transmission. So I don't want to lose my light. I'm going to make my fiber really small. My light is being guided by the environment, but it's still being guided, so I won't lose any of that light. And these fibers can be made really small. So this is an example of a fiber wrapped around a human hair. So we can see that really so human hair is about 50 micron typically in diameter. So you can see how thin these fibers get. And these are sort of examples as well of shapes that you can make with the fibers. You can knot them. That's fine. As long as you have some translation stages, you can make really complex structures, and the light is guided through the fiber. But remember, some of that energy is outside the glass material. The picture with all the dots is a picture of a bad fiber. So when I make a fiber, it's going to be really tiny. I'm not going to be able to image it. It's going to be less than 1 micron in diameter. These dots just indicate it's dirty. So dust has deposited on the fiber. And each of these dust particles acts as a scatterer of light. So if light is coming from the left to the right, it's being scattered, and my transmission will be much lower than what I want. So when I make a good fiber, there should be no scatterers, so no dust particles. So whatever I put in essentially will come out. So usually when we make fibers, they'll have more than 99% transmission. So that's what we aim for. So what are their advantages? Well, here again, I've got some scalings put in. Here's a normal single mode fiber with a very thin core, and then some glass around the glass core. Red blood cells, somewhere around 5 micron. Human hair, as I said, somewhere around 50 micron. And this is a 2 micron taper fiber. So we're really talking small. 2 micron for us is too big. So we typically work some less than 1 micron size. So one of the main advantages I think that we have is if I focus a light beam. So the image on the left is showing me focusing a light beam down to, let's say, 1 micron. I want a really intense light field. And if I do this, I'm going to have a focal region or a Rayleigh limit or a Rayleigh range over which I can view that light field to be really intense. And if we do some rough scaling, we can say that the distance over which the light is focused over the diameter of the light beam is something like 10. Okay, so we can get that quite okay with good optics. Now, in my ultra-thin fiber, I said that this distance here for the ultra-thin part is going to be a few millimeters. So the type of scaling I can get if I want to view this as a focused light is around 10,000. So my light will extend into the environment, but it's still maintained by the size of the fiber. So it's going to be a couple of 100 nanometers wider than the actual fiber size. So you can start seeing that I end up with a really long interaction region. So I can explore things in this fiber that I simply cannot look at if I'm in a really tightly focused beam. The other advantages, they're actually pretty easy to make. So any student coming into the lab learns how to make good fibers within a few weeks. They're cheap because I just need fiber. I just buy the cheapest fiber from Thor Labs or any other company, and I can make these. Because I have such high field intensities, because my light is confined into such a narrow fiber, I can have nonlinear effects just within the silica glass fiber. And at the end of the day, it's just a fiber. So if I want to connect a laser to it, if I want to connect a detector, anything like this is really easy. I just buy some fiber components and connect them. So at the bottom here, we have one of our fibers. Okay, so this is a fiber that we would use for working with cold atoms. goes down to less than 400 nanometers in the waist. And the waist is quite long. Okay, I haven't measured it in this one, but you can see the sort of profile that we have. We start up with the large fibre, very gradually go down to the very thin waist region. Then we go back up to the fibre and then just normal fibre at each end. So what are these fibres used for? They're used in a lot of areas. And people are surprised generally when we say how many areas they're used in. So they can be used as optical sensors. They're used in atom optics. They can be used in plasmonics. So you can deposit metallic structures on these fibres. They're used in optomechanics because they're really, really light, and you can see sort of the photon pressure acting on these fibres. They're used in standard photonics. So when you have an optical coupler, a fibered optical coupler, all it is essentially two very thin fibres where you're going to have the field coupling from one into the other because it's so thin. And I said many areas, and the sort of areas we look at, we put them into cold atom clouds and try to interact with the atoms. We use them as couplers into whispering gallery mode cavities. So you can just see the fibre here. We make other types of cavities on these very thin fibres. And we use them for particle manipulation, so using an optical tweezer type effect. So here I'm just going to talk about one example from the cold atoms and more or less one example from the particle manipulation. So first, let's talk about cold atoms. And I'm going to assume you all know what cold atoms are. So I'm not really going to explain them, but hopefully I will get across to you why we're interested in looking at these. So first question we say, well, why would we care? Why would we have a cold atomic system? So we have a cloud of atoms which are cooled down to maybe 100 microkelvin. Why would we put an optical nanofiber into this cloud? Well, one thing I've said is it's extremely small. Yeah, the size of my fiber is less than 400 nanometers in diameter. So it's not going to disturb my experiment. So it's not like taking lenses and trying to put all of this heavy, bulky optics into my experiment. I'm putting a really tiny thing in. So it's really ease of integration, non-destructive measurement methods. And then the other reason is there are a lot of proposals where people talk about quantum communication. And in all of these, they talk about having standard fiber links between quantum nodes. So the quantum node is where I do my quantum algorithm or some form of quantum interaction, and then I connect these nodes just using normal optical fiber. But to couple this system, which is quantum, to the fiber, I'm going to always have a big loss. So we thought, well, why don't we just make sure that with the quantum system, we have the nanofiber? The nanofiber can then easily be connected to the normal fiber connectors, and we reduce the loss significantly. So it was more or less very much a thought experiment. And we started talking to some of the theoreticians who were working on these thought experiments. And just more or less, that's how all of this work came about. Standing in a room for hours talking to theoreticians. They knew loads. I knew very little, but as an experimentalist, I said, look, the best way to see if it works is to try it, because you can write whatever equations you like. If the experiment doesn't exist, the equations don't mean so much. So we decided, okay, this is the sort of area that we'll focus on. And another reason why, and this is just showing an example with actually a nanofiber in it, is that you can use these nanofibers for quantum memory and for storing light signals. So this is work done by a group in Paris, Julien Laurat. So they had a cloud of cold atoms, and they put one of these nanofibers through this cloud, and they essentially did some EIT, or electromagnetically induced type experiment. And therefore, they put a delay on the transmission of light, where this light was being stored by the atomic system. So we know that we can store light using atoms, and we know that that can create a quantum memory. So there are several ideas which started to indicate that maybe using these nanofibers might be useful. So we work with Rydberg atoms. Rydberg atoms are highly excited neutral atoms. So if we think of a very simple picture of the atom, we have the nucleus, which has a charge of +1. And since we work with alkali atoms, we have a single electron in the outer orbital. We work with rubidium, again, purely historical, because that's what we've always worked with in the lab, and that's what we have lasers for. And the reason why this Rydberg atom is interesting for many people in the quantum community in the last few years is that you have very large long-range interactions between the different atoms. And this can lead to a feature called Rydberg blockade, which I'll explain. You also have large polarizability, so you can have a very good interaction with laser fields, and the atoms can have a very long lifetime. So if you want to do some interaction on your atom, you have a lot of time in which you can do that interaction. So there are a few advantages to working with them. There are definitely some disadvantages to working with them because of the fact that you have an electron which is so far removed from your nucleus, that electron can easily be stripped from the atom, and we can easily create an ion. So that's the main disadvantage from our point of view. So this Rydberg blockade, it's well known, very well established by now. If I have an atom and I want to excite it to a Rydberg atom, so let G be a ground state normal neutral atom, and I want to excite it to R, which represents a Rydberg atom. In order to do that, I'm going to have to choose a certain laser frequency and laser intensity in order to get the right Rabi frequency. So if I do that, fine, I choose my laser correctly. One ground state atom, give loads of energy to it, the electron will be excited, and I'll create my Rydberg state. Now, once I bring a second atom near this Rydberg, so I'm going to make a more complicated system. I now have two atoms, either in the ground state, one in the ground, one in the Rydberg, or one in the Rydberg, one in the ground, or two atoms in the Rydberg. As soon as I create one Rydberg atom, there's a van der Waals interaction between the atoms, and this shifts my energy levels. So while my laser was on resonance to create a single transition, the laser is going to be off resonance for the second transition. So it simply can't happen. Now, this van der Waals interaction is a function of the separation of the atoms. So if the atoms are really close, the van der Waals interaction is big. So I'm going to have a large energy shift. I will not be able to get two Rydberg in the same volume. Okay, so the interaction will cover the volume space. If the atoms are far away, van der Waals interaction will be really small, no energy level shift. I can create two Rydberg atoms. So this creates a system whereby in any volume and space represented by the big circle, pink circles, I have my atoms represented by the blue, my normal ground state atoms, and I can only have one Rydberg excitation. So effectively, this is called a superatom. So the combination of the ground state atoms and one Rydberg atom can be used as a qubit within a system. And there are many, many papers, both experimental and theoretical, using this Rydberg blockade for quantum information. So for us, we want to incorporate a fibre into this system. And the questions we had, okay, fibre is a dielectric material. If I bring a dielectric material next to an atom, I risk ionizing that atom because the electron is so far from the nucleus. So it's weakly bound to the nucleus. So any form of charge that builds up on my fibre could strip that electron. So the first thing was, can we create these Rydberg atoms? The second question then was, if we can create the Rydberg atoms, how high an excitation can I actually have? So the higher my excitation, the larger I can view my atom. So my ground state atom is tiny, it's a few angstrom. And as I start exciting it larger and larger n value, my electron is moving further and further away, so my atom, we can view it as getting bigger and bigger. So there must be some situation where my atom is too big and it starts to really engulf my nanofibre. So we started to question, okay, where is the limitation? And then within my system, I can have s and d orbitals, so different orbitals for the electron behavior. So this is my experiment. I have two photon transition to get to my Rydberg energy level. So my first photon is at 780. That's fine. That's a standard D2 transition within rubidium atoms. My second photon is a blue photon. I then scan the frequency of my blue photon in order to choose which N value I have. And I can choose D or S states, again, depending on the frequency and the detunings of my lasers. I'm limited to S and D orbitals because of the selection rules. So I simply cannot choose P orbitals, okay, because I'm starting off from S to P. So then from P, I can only go to D and S. The S orbital is this nice spherically symmetrical orbital. People like working with it because of the spherical symmetry it has. The D orbitals have 5 possible symmetries. So I don't know how to describe these, okay, it's sort of, think about the orientation of a double dumbbell, and then this one here in the middle is very different. Okay, so here I don't see really any symmetry between the possible orbitals that can be occupied by the electron. The experimental setup is quite simple once I have my cold atom cloud. So I immerse one of these nanofibres into my cold atom cloud. I send a lot of different laser beams through the cloud. So I send, let me take that one away to simplify it. I first of all have to send this blue light in order to do my Rydberg transition. So that's what we see as the blue light going through the fiber in a single direction. I also send red light. This red light is not the 780 nanometer transition. This is an additional light beam just to heat up my fiber. I don't want my fiber to be the coldest thing because my atoms will just stick to it. So this is just to heat up the fiber essentially. And this transition here, the 780, just comes from my magneto-optical trap. So I need to use 780 in order to laser cool the atoms. Because my blue light is going through the fiber, the only light in my system, which is blue and which will allow me to make the Rydberg transition, has to be in the evanescent field. So this light that's being guided in the fiber, but outside the fiber. So it's interacting with the atoms in the evanescent field, and it's only going to interact with a very small number of atoms here at the waist region. And then for my imaging, I can either take a photo of my atom cloud and see how it changes, or I can use a photomultiplier tube and actually get a value of the light number of atoms in the cloud, essentially. So here's my experimental setup. My atoms have a temperature when I start of about 100 microkelvin, somewhere around that region. I have my magneto-optical trap. It has 6 laser beams. You just see 4 here. The other one goes in and out of the plane. I have my optical nanofiber, and here's a photo. So here's my cold atom cloud of rubidium-87, and you can see the fiber here going through the atom cloud. And then in the vacuum chamber, I mentioned we have to put the blue light through the fiber so you can see some of the blue light scattering. So where you see it scattering is a large part of the fiber. Where you don't see any blue light is the nanofiber part, and that's the place where the interaction will happen. So I need to first load my magneto-optical trap and get some cold atoms, and then I turn on my blue light to do the Rydberg excitation. So here's just the loading scheme for my different lasers. 780 nanometers, I turn on my cold atom cloud, and I leave that on during the full time. At some point, after 8 seconds, I turn on my blue laser. So my blue laser is going to cause either Rydberg excitation, or there might be other losses in the system. So I'm just going to lose some atoms from my magneto-optical trap. And then this one is the red laser beam I said, always going through. It just heats up the fiber, so it's not cold in the chamber. So this is the typical signal I get over time. So you'll see it's the same time scale as for my timing program. So I turn on my magneto-optical trap. Atoms start getting trapped and cooled until I reach saturation. So no more atoms can enter the magneto-optical trap. At this point, I turn on my blue laser beam and I see a dramatic loss in atoms from the magneto-optical trap. And the signal I look at is actually the remaining atoms. So I do this many, many times and get some average signal. And I see how this average signal will change depending on the frequency of my laser. Because remember, different laser frequency will tune to a different Rydberg level. And these are the sort of signals I see. So here I'm scanning my Rydberg laser, so for the upper transition, and I'm looking at what happens to the number of atoms left in my magneto-optical trap as I'm scanning the laser. And we can clearly see that there's a frequency dependence on the number of atoms in the trap. So if there was, this is a signature that we're definitely exciting Rydberg atoms, okay, because the fact that it's frequency dependent. There are two peaks here, or dips. We can explain these two dips by some dressed atom approach. So you have the atomic, you've got a two-level systems, you've got a middle energy level, you're having some type of shift depending on the detunings of the laser beams relative to my middle level. Or I can view it as the splitting of that middle level due to the intense beams. So I can view it as an outlier tones. But these two essentially dips for the D level are quite well explained. So this, we started showing that we have 29D, so we can excite up to n equals 29. Here's for the S level, the signal is much bigger, much more dramatic behavior when we're looking at the symmetrical orbital. Okay, so we can excite Rydberg, 29D, 29S, not a very high excitation. So the next thing we wanted to see was how far can we actually push this? So how large Rydberg atom can we excite next to the nanofiber? So here we're varying the principal quantum number that we access. And again, we're looking at the remaining population in the magneto-optical trap when we turn on that blue laser. For ns1/2, so for my s orbitals, when n equals 55, suddenly my experiments stop. I lose my signal. No matter what I try, I can't do this again. I repeat it, I go back down to any of these earlier n values, I simply have lost my signal. I've effectively destroyed my fibre. N equals 65 is the cutoff point for ND 3/2, so I can push it a bit further. And ND 5/2, which has the most asymmetry with respect to the orbitals, I can push it the furthest. So the highest excitation I can get at the moment is about n equals 68 for the ND 5/2 energy level. So this region here, once we can no longer excite S and we can still excite D, we're assuming that effectively we have stripped the atom, the electron from the atom for the S, but we're still able to excite D, and then when we get the cutoff points for these, we're stripping the electron. And once we strip the electron, we're left with an ion. This ion ends up causing a localized charge on the fiber, and we simply can't work with it, okay? Energy level shifts become crazy. So what is the size of the atom? So when I'm working with an n equals 29, my atom is about 50 nanometers in size. When I'm working with n equals 67, my single atom size is about 300 nanometers. Okay, this starts becoming pretty massive compared to a normal atom. So let's see what that means for my fiber. My fiber diameter in these experiments is about 350 nanometers, okay? Sometimes maybe closer to 300. So when I'm exciting my atom, and I'm exciting it in the evanescent field from the fiber, which extends by a couple of 100 nanometers, at some point my atom is so massive, I can view that that electron will just hit the fiber. When it hits the fiber, it'll cause this local ionization, and I've simply destroyed the system. I've killed the Rydberg, no more Rydberg excitation, and I've caused this charge on my fiber, which dissipates after a few weeks, okay? So I can't do a project anymore, but I wait a few weeks and I can redo it. If I think of my s orbitals, looking at the probability density of the electron in the s orbitals versus the d orbitals, I start seeing the asymmetry appearing in the d orbitals. And what we're hypothesizing, therefore, is that the s orbital, if it's really looking like this massive sphere, I really hit a point where I cannot do excitation. Whereas for the d orbital, I can push that a bit further, because you can imagine that there are scenarios in these d orbitals, if we imagine that all of them had somehow equal occupation or probability of existing, there are scenarios where they may orient so that the electron wouldn't be hitting the fiber. So for us, it looks more interesting, therefore, to work with D instead of S. this symmetry of S is actually problematic for us. And to try to really understand these surface interactions, what's actually happening when the atom is so close to the fibre, we looked at how much we would have to shift that blue laser in order to be able to still do the Rydberg excitation. That's the blue curve. And how much is a Casimir-Poldner shift, so subcategory of surface interaction, but with the atom and the dielectric. And we see that as we go further from the fibre, Casimir-Poldner becomes 0, so we don't really have to worry about it. And as we go further from the fibre, the Rydberg transition, so the shift on my detuning, almost becomes 0. So when these shifts are small, we can work with it. But if these shifts are massive, it becomes extremely hard to do the Rydberg. And similarly, we looked at sort of the Rabi frequency, so how to that transition, the upper excitation and the total detuning. And again, we saw some massive shifts if we're too close to the fibre. And if we go a couple of 100 nanometers from the fibre, it looks like we can operate there. So essentially, experimentally, we cannot generate Rydberg atoms really close to the fibre because of these surface interactions. Now, we're loading the system from a MOT, so atoms are distributed, and most of those atoms are near the fibre. It has a Gaussian distribution. So now what we're doing is making sure that most of our atoms are far from the fibre. So looking at this 2-photon resonance, so again, looking at this principal quantum number, how is the shift happening? So what is happening to these frequency shifts? And again, we can see that for S level, we really have massive variation in our signal compared to what we have for the D level. So again, working with this symmetric S really seems to put a boundary on what we're doing. Okay, so now the next step, therefore, is to define the position of the atoms relative to the fibre rather than having them all moving around everywhere. And the way we do this is using fibre-based dipole traps. So if I think of one of these fibres and I pass both red and blue light through it, the red light will act as an attractive potential and pull atoms towards the fibre, whereas the blue light acts as a repulsive potential and will push the atoms away. So when I combine these two fields, I'll end up with an overall potential. So here's just the intensity of my field. These sharp spikes are at the surface of a nanofibre. This is a simulation. So you can see how I'm putting more light into the evanescent field region, and that will depend on the wavelength of my red and blue detuned fields. And the overall potential has a little dip, a couple of 100 nanometers from the fibre surface. So if I now trap my atoms a few 100 nanometers here using these dipole traps, instead of the overall distribution I get from magneto-optical trap, I should be able to control that surface interaction and minimize it as much as possible. So there are experiments on this. We have done experiments. So this is a well-known technique. It's been around for 15 years. People have trapped cesium. People have done more complicated trapping of cesium, and they managed to get about 2,000 atoms in cesium, and you get about 300 atoms in rubidium. So then in order to push that a bit more, to try to get more rubidium atoms, because that's what we work with, and we always want more signal, we adapted a machine learner that was being used in Australia for atom trapping, and we adapted it for the fibre. So in this machine learner, it's based on neural networks. So we define 19, in fact, experimental parameters for our laser cooling system. So these experimental parameters are things like frequency detuning, magnetic field, intensity of lasers, and so on. And we look at the transmission through the fibre. And if we have a high transmission through the fibre, it means we have very few atoms interacting with the probe beam. So we want to minimize the transmission, and we define this as the cost function for our machine learner. When we minimize the transmission, it means we have maximized the number of atoms. And if I do that and I look at transmission through the fibre, so that's tuned to an atomic resonance, red is manual detuning, purple is with the machine learner. Indeed, I can see I get my transmission down to 0, which means all the light I'm using to probe the atoms gets absorbed, which means I must have a lot of atoms interacting with that probe light. And similarly, I can look at the optical depth. So this is a parameter which is really useful in atomic physics. So it tells us more or less how much light is absorbed by a single atom. And again, the red is if I do manual tuning of my atomic traps, and the purple is if I let the machine learner just tune everything. So the sort of numbers we got, instead of 300 atoms trapped, we got 1 to 450. Slightly colder temperatures when we brought in our machine learner, and we almost doubled the optical depth. So this allows us now to position atoms at a certain distance from the fiber surface, and the next step then will be to do the Rydberg excitation, where we know how far we are from the surface, and hopefully then go to higher n. So the ideal thing would be if we could get to n equals 100. So the other application I'm going to talk about is microparticle manipulation. So this is based on near field optics, and we just want to be able to work with any particle. So this can be a protein, this can be a cell, this can be a test particle. And of course, we always work with test particles because they're the easier ones. And what we're doing is an optical tweezer technique, but we've extended the optical tweezer technique. And of course, some of you are probably working on optical tweezers and optical trapping and know what these are. So we're using a very, very tightly focused laser beam, and due to field gradients and intensity gradients, we end up trapping particles in the focal point of the tweezers. So here the typical particles will be a couple of micron in size and made from polystyrene or silica. And of course, Arthur Ashkin won the Nobel Prize for this. It's already so long ago now, 6 years or 5.5 years ago. So for optical tweezers, these are the sort of experiments people can do. So I talked about a single focus beam. You can have many, many focus beams. You can either physically have many beams, or you can use some type of spatial light deflector or modulator to move your beam really, really quickly. So when you do this, you get you can play games with your optical tweezers. So here they're playing Tetris with their optical tweezers just by moving the focal point of multiple laser beams to wherever they want them. And these would probably be, again, something like a 3 micron polystyrene, probably. People also use optical tweezers for living cell manipulation. So zebrafish are used always as some form of test creature. Their larvae are transparent, and that makes them really good test bed for imaging or anything where you want to work with a transparent medium. So these zebrafish larvae have a long tail, and by shining light on a certain region in the front of the fish, you can affect the direction in which this tail will move. So here's a video showing you. So they can play with this tail movement, putting in different intensities of light. The red dot shows you where they have shunned the light. Depending on the intensity, the tail is shifting more and more. So for 100 milliwatts, it's hardly shifting, whereas for 400, I'll just play that again. It's 600, there's a really dramatic response, 400, less response, and so on. So I said optical tweezers are really well-established technique now. But there are some limitations. So the force in an optical tweezers has 3 terms. And if we look at these terms, the first one, which is the gradient term, is dependent on the cubic radius of the particle you're trapping. The scattering depends on the radius to the power of 6. And then we have a polarization gradient. So if you've got a gradient in your polarization field, you need to take that into consideration. So if my particle gets smaller and smaller, if I look at this gradient term, so it's essentially proportional to the intensity of the light. So if my particle is getting smaller and smaller, to have the same term here, I'm going to need more and more light power, or focus light more and more. Focus light I can't do better. Okay, I hit a diffraction limit. So if I go from 100 nanometers to 10 nanometers, my gradient force will reduce by a factor of 1,000. So similarly, I'd have to have an increase in my power. So we can deal with this using what's called plasmonic tweezers, but I'm not going to go into them today. The other problem happens if the particle is non-homogeneous. So in optical tweezers, usually, not always, but generally the particle is fairly homogeneous. And that allows us to trap it pretty well, pretty stably. But if we want to do something with needing a very strong gradient, the optical nanofiber proves to be an option. So I'll show you how this works. So let's think about microparticles, 3 microns in size. And here I have a standard optical tweezers type behavior. So standard optical tweezers, my particle gets pulled into the focal point of my light beam. And by doing time sharing, so I just move my light beam really quickly to make whatever type of pattern I want, I can generate any type of structure. And you can see the small Brownian motion of the particles still within the optical tweezers. These are for 3 micron. And the other thing is these particles have no free will. So essentially they have to do what I tell them. They have to stay where they are. If I use an optical tweezers, and this is from very early video, it's probably about almost 20 years old by now. So here I'm sending, the particles are the same, and I have an optical tweezers, and the particles are being pulled towards the fiber by the gradient of the evanescent field. And then they're being propelled along the fiber because I'm just having light coming in from the left to the right. Okay, so all that's happening is pushing particles due to this. In principle, I could tie a knot, the particles would follow the circular loop. So what we started looking at was trying to do this in a better way. So first of all, capture your particle using an optical tweezers, drop it next to a fiber, and when it's next to the fiber, then let it move. So it'll be a single particle, and then try to drop 2 particles, 3 particles, 4 particles, and study the forces between these particles. Depending on the size of my particle, as it comes into the evanescent field, it'll interact more with it. So I should see a change in the transmission through my nanofiber. So here's looking at the transmission. So red is a smaller particle compared to blue. So the big particle interrupts my evanescent field more than the smaller particle. And these are the cleaner experiments where I can control how many particles come next to the fiber. Here I'm just putting 1 particle next to the fiber. I can put 4 particles, I think up until 7 is what we have managed. Here's a video of 6 particles next to the fiber. So the student was very patient, trapping 1 particle at a time, releasing it, bringing the next particle, and trying to keep them all trapped in the gradient field due to the evanescent field from the fiber. Here we can see where we're starting working with circular polarization. So the particle starts orbiting around the fiber depending on the polarization of the light. They're not moving along the fiber very much because I'm now putting 2 light beams through. So the linear momentum is being more or less cancelled, and all they're ending up with is the spin angular momentum, which transfers into an orbital motion of the particles. And what I really like here is that they go into phase. So you can see when they're going behind the fiber is at the same time, when they're in front of the fiber is at the same time. So there's a lot of interesting light scattering effects going on here. And here you can see if I have 3 particles, more or less 2 are dancing together. The 3rd particle comes in, they start switching partners. So 2 always want to go into phase, and the 3rd particle always somehow gets ignored. So it's like dancing. So 3 people can't really dance together. But
so does this depend on the nature of the particle? This is very fascinating.
Moment we did these experiments quite a long time ago, and then we spent a long time cleaning up the optics. So the below picture is quite old, and the upper one is much cleaner optics. So we're only now going to start studying really what's happening. So these are just polystyrene. Yeah. We haven't looked at, it's really interesting to try to understand really what is happening now between these interactions. Why, when we have the 3, how do they choose which one they move with, and so on. Okay, so that's sort of showing you little cute experiments. So then I thought, okay, well, here's a case where we changed our particle. I said, okay, let's make our particle into a Janus particle. So the type we choose, a Janus particle is a particle consisting of 2 different media. So we're choosing a spherical particle, and it's made from silica. And we coat half the particle with gold. And we spent a lot of time trying to make these particles. These are viewed as active particles because now we have two materials. And the gold, for example, will heat up more in a light field than the silica because it might absorb more radiation. So in general, when people work with Janus particles in a Gaussian beam, so this is not very tightly focused, okay? This is a big Gaussian beam. Silica particles congregate in the area of maximum intensity. So they're going to congregate here in the center of my Gaussian beam. Whereas Janus particles tend to gather at the highest gradient region. So they gather in the outer edge of my Gaussian, where they see a different type of behavior. So the peak field gradient. So in the evanescent field, we essentially have a combination. If we're using a Janus particle, we have this combination of silica and gold. Where are they going to cluster? So how will they behave next to the fiber? I'm actually going to skip the fabrication because that's really technical and I'm keeping an eye on the time here. So the experiments for these, all of these particle around the fiber, they're really simple experiments to set up compared to a cold atom experiment. To get the statistics is really slow because you've got essentially a dirty system. Yeah, atom systems are clean once you've built them. These are dirty systems. So we start off with a solution of Janus particles and normal silica particles, same size. We try to make sure their size matched. And we put them nanofiber in there. We use the optical tweezers. So this beam 3 is indicating an optical tweezers to select a particle and move it next to the fiber. So we'll either select one Janus, one silica at a time. So far we haven't looked at multi-particles. The PCs on either side allow us to control the polarization of fibers. So this means we will know whether we have circular polarization or linear. And all of these experiments, we just want linear motion. And then we just image what we can see. So these are sort of the types we do. So we can have vertical polarization, and this just tells us what our orientation of linear polarization at the fiber is. Silica and Janus, the two different types of Janus, one has a layer of 10 nanometers of gold, and the other has a layer of 20 nanometers. Purely technical why we chose these. No scientific reason, it was purely technical in order to be able to trap them. We can also do horizontal polarization. So by looking at the orientation of the particle, we can know exactly which polarization we've set up in the system. I'm going to pause this video. So this is a Janus particle. I know that because I can start seeing a dark and a bright region on my particle. First thing I do, beams in each direction, trap my particle, then turn off one beam to push my particle to the edge of my imaging, then let the particle move along with linear momentum. So this is just trapping my particle. All beams are on. I'm now going to turn off one of these beams in order to move that particle to one side. So that's just to set up my experimental measurement. Now I'm doing my experimental measurement. So from when it starts going from left to right, this is when I start monitoring my velocity of the particle. So when I do this, this is my Janus on top, a silica particle on the bottom. The Janus always moves faster than the silica. So if I just make them move at the same time, you can see the Janus always moves quicker. And I can look at my electric field distributions. And we can see that in the Janus particle, because of the presence of the gold, the field will be very differently distributed compared to the silica. And what came out was that if I look at the orientation of my Janus particle, so how is this gold cap oriented compared to the fiber? It's almost always constant. So whether I have a 10 nanometer gold layer or a 20 nanometer gold layer, this shows me the orientation angle relative to my fiber. This is a theory we developed and an experiment. There isn't much variation. So it's essentially always about 27, 28 degrees. So it acts as a sail. It points away from the laser. If I change my power, the same thing, almost doesn't affect the orientation. This is a little bit surprising because you would expect more heating, but we're limited on how much power we can put through because we don't want to boil the water. All these experiments are done in water. Here you just see different cases, always the Janus followed by a silica, so Janus on top, silica, for different thicknesses of the gold. So we then just analyze these images to see the motion. So what's actually happening? So I'm trying to understand the temperature. So from the results we got and the theory we got, it looked to us, these circles here indicate this is a Janus particle like we tried to create. So half of the material is gold. To match the experimental data, this would indicate we have a temperature change of 535 degrees when we do these experiments. We know that's impossible, okay? We wouldn't have any water left. If we only have a quarter coating of gold, so an uneven distribution on our Janus particles, we'd have a temperature of 22 degrees change. And if there's no gold, the temperature change in the water would be about 1.5. So then just all of this is theory and experimental simulations. So these are theory showing you essentially what would be the temperature I would get depending on the size of the gold cap. So if it's a half gold cap, this is where I would be, the one value. Quarter gold cap would be down here somewhere. Okay, so the arrows just indicate the line showing you this ratio. And our experimental data are lying always somewhere here, so very small temperature changes. This is showing the force along the fibre as a function of the power that we apply. This is showing the force perpendicular to the fibre as a function of the power that we apply. And you see all the curves follow very, very similar trends. And then here again, theoretical simulations, and the red and the blue are our experimental data. So our experimental data for 10 nanometer gold Janus particle fits around here, and our experimental data for the red fits around here. So we've got a pretty good agreement between our theoretical model and our experimental model as to what's happening temperature-wise. So effectively, our Janus particle is lying somewhere between this quarter coating and the half coating. Here we're looking at how this varies as a function of fibre size. So again, the straight lines are the theory and the data points are experiments. So again, you can see that our theory is matching our experiments pretty well. This is an enhancement factor that I'm plotting here. The enhancement factor is essentially how much quicker my Janus particle will move compared to my silica particle. So that's where we finished up. Now we're rebuilding the experiment with a new student, and we're looking at different materials. So this comes back to the earlier question. So we're starting looking at silver instead of gold, different shaped Janus particles, example, if we had a dumbbell instead of a sphere. And also we really want to look at this so we can work they take years of data taking. So we have to have really, really good statistics in order to be able to present these data. And we've also done work on using these fibres and building if they're in blue, they've now gone to work with industry. If they're in black, they're still working in universities. Mark, I didn't know what to call him because he's working for a funding agency. So is that industry? Is that government? It's hard to say. And interestingly, I would recommend if you're looking for a speaker, Ravi Kumar, he did a PhD on this topic in my group in the cold atoms, and he has now set up his own company in Singapore on atom interferometry. So he's a very interesting speaker to invite. So I'd like to thank you for your attention.
So if there is any question, please feel free to ask.
Yeah, I have a question. Yeah, wonderful talk. Thank you very much. If I understand correctly, the way in which the angular momentum comes into picture when you have such kind of fibers is is initiated by the profile of the laser what you introduce into the fiber, right?
Oh, no.
Oh, okay.
So we just use Gaussian beam.
Just Gaussian beam. Okay.
Just Gaussian beam. So when I started all these projects before moving to Japan, I thought I would have to use higher order modes propagating in my fiber. And we have had numerous projects on higher modes in order to try to get some orbital angular momentum within my beam.
Mm.
But at the same time, in the last few years, there's been a lot of theoretical work done on what's happening with the angular momentum in a non-paraxial laser beam. So this is like tightly focused optical tweezers, or this anything through a nano aperture or our nanofiber. And it turns out that normally we think of spin angular momentum. My particle will spin around itself. Orbital angular momentum, it'll move in some orbit because I've got something like a Laguerre Gaussian beam or some beam carrying orbital angular momentum. And that's fine. We think in that way. But the reality is that there's a certain parameter space where we cannot separate out spin and orbital angular momentum. It's just angular momentum of the system. For the fiber experiments, if I do a specific size of particle has to match with a specific size of fiber to reach this parameter space. So even though I put in to the fiber circular polarization, at the waist of the fiber, I will end up with this canonical expression for angular momentum, which is a combination of orbital and spin. So I haven't just, the circular polarization will not just give me spin, it'll also give me orbital. So this is how I'm able to see the orbital motion. Can I see the spin motion? We would need inhomogeneous particles. Okay, so we've no way of seeing, do these particles also have some type of spin? So the project we're working on here on transverse spin, it's a little bit different, but it's somehow related. There we're using liquid crystals because the liquid crystals have some chirality, and we can also freeze the liquid crystals. So we can do some processing on it to remove that chirality so we can exactly compare the equal particles. Yeah, so it's just, so the experiments turn out to be easier than I had originally thought. Yeah.
Fascinating. Which means that the nature of the polarization, what you introduce into the fiber, has an important role to play here, right?
No, so the only thing I care about is my polarization at the waist. So I monitor my polarization at the waist, and I play with polarization compensation at the output to make sure I have the right polarization at the waist. So for the Janus, it was linear polarization I wanted at the waist, but in these rotational ones, it's circular polarization at the waist. Yeah.
Thank you. Thank you very much.
If there is any other question.
Yes, I have a question. So if we put the Gaussian beam on a liquid crystal droplet, having the different refractive index on that liquid crystal droplet, so what is the effect of the Gaussian beam on that droplet?
Oh, I don't think it'll have any effect because of the size of my liquid crystal droplet. Yeah. I think you're just going to, so if you're Gaussian beam, you'll depend on your circular. In a normal Gaussian beam, I would guess it will depend, you will get some circular orientation of the droplet, some spinning of the droplet, depending on the polarization. Okay. So here in our experiments here, where I call it the demonstration of transverse spin, so this is an ongoing experiment. We trap the particle, the liquid crystal particle, first of all, in an optical tweezers, and we choose the polarization of that optical tweezers, okay? That then causes a spin on our liquid crystal, and then we also use a feature from the nanofiber in order to detect this spin, okay? So then when we change the direction of our circular polarization, we should see an opposite effect on the spin, but it's a bit trickier than that. But that's the easiest way I can explain it without having any more measurements here. So all these S's in my diagram here, these are all indicating different spins. So the blue S's here are coming from the optical tweezers. So this is just the spin I will have on my particle from circular polarization in my optical tweezers. So that'll be a tightly focused Gaussian. And then these S parallel and S perp are spins that are on the light propagating through a nanofiber. Okay, so then effectively I'm combining various different spin components to understand the motion of the particle. But just in an optical tweezers is quite simple.
Okay.
Does that answer you?
So what? Yeah, it's right. So just like if we consider that the Janus particles in a Gaussian beam, they accumulate at a higher intensity. So is it possible that the liquid crystal droplet that are of passive nature, it will accumulate at the higher Gaussian density?
Okay, so for the Janus particles, that was not a focused beam, yeah? So it was just a normal beam following a Gaussian profile. The Janus particles, if you remember, gathered around the edge of the beam. Yeah, the silica particle went into the maximum intensity, yeah? So for the liquid crystal in just a big, like if I had a 20 micron Gaussian beam and put liquid crystal in it, I don't know, do the experiment. It's not so hard, you need a laser liquid crystal, yeah. You don't even need a good...
just recently I was...
Yeah, you don't even need a good lens.
I was thinking about this.
Okay.
Yeah, okay, thank you.
I have a question. Thank you for the talk. So, essentially for all your experiments, you used a single mode fiber. And what would happen if you use perhaps a multi-mode fiber?
Yeah. So if I use a multi-mode fiber, it's going to be a little bit bigger, okay, because my parameter for ensuring what modes propagate in my fiber, it'll shift my V plot, if you know V plots and fibers. So I'll have a slightly bigger fiber. When I have a slightly bigger fiber, it means my evanescent field will extend less, okay, but it'll still be there. And what I can then have in this case is interference between different modes. So if I do a higher mode fiber, I will never be able to get rid of the fundamental mode. I've done many, many experiments on this. There will always be some, even if I shine in a higher mode, like try to get some matching between a Laguerre Gaussian and a mode in the fiber, there will always be excitation of some of the fundamental mode in the fiber. And then let's say I have another mode. There will be some interference effect between those modes, and then they can create little interference trapping sites along the fiber. But normally we end up with a little bit messy mode structure when we do that. So we used to do a lot more on having multi-mode, so up to 4 modes, but then we dropped back because we decided actually with a single mode, we can see a lot of the things we were looking for from the higher modes, such as this orbiting. We thought we would need a higher mode to see this, but we actually get it from the single mode because of the fact that we shouldn't talk in terms of orbital and spin as separate components of angular momentum in this configuration. So from the interference of the modes, I think we can get some interesting combinations for atom traps, for example, but it's a bigger fiber, so you don't extend the evanescent field as far into space. Does that answer you?
Yes.
Yeah, but some advantages, some disadvantages, yeah.
Yes.
But it's possible. Possible.
But essentially, you would have some speckle-like feature in the evanescent field as well, right?
No, I'm not sure if there's any speckle-like feature. I mean, I've never noticed any. We don't really image ever the evanescent field itself because it's not really obvious. I have a collaborator in Israel who's trying to do that by putting some dyes into materials and trying to see some excitation of the actual field. But I think it would just be more like an interference effect, in fact.
Okay. 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 Thank you. Thank you very much.
No problem.
Yeah, ma'am, can
Yeah.
you please go to the slide number 32?
32 here. Yeah,
Yeah,
this
so
one's a
ma'am,
bit.
here in the top case, it is the coating is like almost the half coated.
So the top one here
Yeah.
is the half coated. Yeah, what we assumed we had. And the next one is just a quarter coating, and the bottom one is no coating. So if I go to the fabrication slide that I skipped, okay, here's my fabrication slide. So here you can see my particles that I've made, okay? So gold, well, that people in my group made. Gold coating on a silica sphere. But we assume that we have 10 nanometer or 20 nanometer thickness, but that's not the reality. If I think I have a sphere and I drop gold on it, the coating at the top of the sphere will be thicker than the coating at the edges. So this sort of half coating, quarter coating, it's impossible in COMSOL to do thinner coating. Yeah, that the coating is getting thinner and thinner. That's just impossible. This was the nearest we could do. So the half coating would be assuming that we have a uniform coating, uniform thickness everywhere, whereas this quarter coating is assuming our coating gets really thin at the edges, if that makes sense.
Yeah. Okay, ma'am. Can you please go to the slide number 30?
Which one? 30?
30.
Yeah.
Yeah,
Here.
so ma'am, here you have used three lasers, three beams, like two from the optical fiber and one from to trap at the position. So ma'am, like, is there some difference between the other two, like beam 2 and beam 1? Like, are you using the same laser, same power, everything?
So we try to have the, let me stop this video so I can show you, bring it back here. They should have essentially the same power so that the particle has no transfer of linear momentum, okay?
Yeah.
So they're going to be the same power, and their polarizations should give me the correct polarization at the edge. So I can't say what the polarizations are until the polarization at the waist. That's all I care about. I don't care about the polarization until I've gone through my compensation components. So their combination should give me the linear polarization here, but they should have the same power. Yeah.
Okay, ma'am. So, ma'am, in this genus kind of particle, you mentioned that the velocity of the propagation is high.
Yeah.
So why that is so?
So we estimate that this is because there is a heating of the gold cap. Okay.
Yeah.
So the wavelength that we use, the thickness of the gold is 10 or 20 nanometers. And if I remember correctly, gold for the wavelength we use, which is, let's say 1064, has a skin depth of a few, maybe 5-6 nanometers.
Yeah, around that.
So there's certainly some of the radiation is going into the gold. We presume that therefore heats the gold slightly and creates some type of thermal gradient probably. But the thermal gradient is not massive, okay? Maybe 10, 20 degrees change, certainly not 80, certainly not 100, okay? So there's some heating effect going on due to the gold, and this is then enhancing the motion.
Okay. And ma'am, the laser that you are like let the laser go through the fiber, nanofiber. So if you change the intensity, what will happen? Will the propagation velocity increase?
So if I increase the power, the velocity increases. Yeah.
Okay. And ma'am, the last question. Actually, like you have used silica particle without coating, silica particle, genus kind of silica particle. So did you check if you with the polystyrene particles? Like what
Yeah,
does
so
it
we
show?
did work with polystyrene. So you have to get the gold coating on it, okay? So there's actually, it's not gold directly on the dielectric. We have a very thin layer of ITO in order to act as an adhesion, extremely thin layer there. And just in general, we find that the silica works nicer in the fabrication than the polystyrene. Okay, easier to purchase the base particles. So we buy the silica, easier for them to be more uniform because we want all our particles to be the same size, and easier generally to trap in the evanescent field.
Okay. Yeah. Thanks.
Yeah. Okay.
If there is any other question. Okay, there is no. So with this, we would like to thank Professor Síle NIC CHORMAIC for such a wonderful presentation and giving us the opportunity to interact with you. So yeah.
Thank you very much for the chance to present our work. Hopefully it's useful.
Yeah.
Okay. Thank you.
Thank you very much, Sheila.
No problem. Bye. Bye. Bye.